Hi friends, so today we start Fortran tutorial lecture 5, and today I'm going to introduce the concepts of vectors, matrices and tensors, how you can implement these in Fortran, and we are going to write some simple programs to illustrate these concepts. So I'm Dr. Ganguly. Now what you do in Fortran is that you have a statement known as the dimension statement. And the dimension statement is essentially used to declare that a certain variable is a vector. For example, here I have defined x as a vector of size 3 and y as a vector of size 3. So essentially this dimension statement tells the compiler that x and y are vectors and they have dimension 3. Now let's write a simple program to calculate the dot product of two vectors. So let's say we have vectors x and y here. X is 1, 2, 3, y is 2, 4, 6, and we want to find the dot product. So what we can do is we can create a do loop. Do I is 1, 2, 3, and I can say xi is I into 1 and yi is I into 2. I have put 1.0 and 2.0 to make sure that the I here is converted into floating point. Now you know that the dot product would simply be 1 into 2 plus 2 into 4 plus 3 into 6. So to do that, what we do is that at first we declare that xy dot is 0. That's the dot product of these two vectors. And then here I put the statement that xy dot is xy dot plus xi into yi. So what this statement is going to do is that it's going to sum through this particular value between I is 1 and 3. And so then I print out the values of I, xi and yi, and then I end the do loop, and finally I print out the dot product or the scalar product of these two vectors. So let's check this out in the compiler. So here I have put this in the compiler, and here the output has come. So essentially it has printed out the value of x here, that's the first vector 1, 2, 3, and the value of y here, that's the second vector 2, 4, 6. So you see x and y were mentioned here in the print statement. Now it's also printed out the value for the dot product, and you can calculate the dot product as 1 into 2 plus 2 into 4 plus 3 into 6. So that's going to give us 28, and 28 is what I have obtained here. Now of course you can see that when we print things out like this is typically known as an unformatted print statement, that is I'm giving star. Then it gives me too many decimals in many cases, especially if I'm dealing with floating point numbers. So there may be some better way to print these things out so I do not have to carry all these decimal places. So I'm going to take the same program and give you what is known as the format statement. So essentially when you use the format statement, you are essentially printing out the variables using a particular format. So here for example I stands for int, f stands for decimal or float, h is something you use to print character, and x is blank space. So let's take the first print statement here. So for example I have to first put a number here, so this number links this print statement to this format statement here, and then I print out I, and I print out then xi and yi. And here in the format statement I have clearly mentioned that I is an int of size 2. Then we have a blank space. We have two blank spaces, 2x. I have f 5.2, so I want to print out the float to 2 decimal points, and the size of the total thing is 5. I again have two blank spaces, and again I have the float 5.2 here. So you can see here the printout comes like this. 1, there is some blank space, there is a 1.00 and a 2.00 here. So I am able to print to only two decimal places here. Similarly, in the last format statement here, the print format statement in the case of xy dot, I want to print out a particular string here. So I use this h here and I specify 15h as the size of this particular string, and then I get dot product is 28.00 because I have used f 5.2 here, and again I have introduced a blank space here. So using the format statement you can print your output out more clearly. It will look better. And so you do not have to get all the decimal places which you get in the unformatted output. Now, in some cases, what happens is that when you print out the floating point numbers, what may happen is that your numbers may be too large or too small. So very often what is done in typical Fortran programs is that you try to print out in terms of exponentials. So essentially instead of f, we use e here for the floating point numbers. And so what this tells you is that, for example, 1 is written as 0.1 e to the power 1, 2 is written as 0.2 e to the power 1, and so on. So through this particular nomenclature, you can deal with very large and very small numbers. And in many cases, this is very useful because you do not have to define the size of that f value in each case. So for example, f5.2 would not work if your number is a very large number. So that's something to keep in mind. So now let's turn to matrices. So essentially, if you want to define a matrix in Fortran, you again use the dimension statement and you say A is a matrix of size 2 by 2. So it's written as A bracket 2 comma 2 bracket close. And so let's try to define a simple matrix here. So I again create a do loop, do I is 1 to 2, do j is 1 to 2. I close the do loop here and then I write aij is I into j is 1, I into j into 1. So you can see that if we construct this out, I'm going to get 1 into 1, 1 into 2, 2 into 1 and 2 into 2. So it's going to give me the matrix 1, 2, 2, 4. And here I'm using the format statement. So I want to print out these as I3, I3 and F5.2. So essentially I and J are int and of course A is float here. So let's try to run this program. So here I have got this program and I have run it, and you can of course see that the values of I, J are being printed out here, 1, 2 and so on, and also the value of Aij corresponding to the values of Ij. So again, you can clearly see that the matrix is quite easy to define as far as Fortran is concerned. Now let's say I wanted to do some additional calculations. I wanted to find the determinant of a 2 by 2 matrix. In that case, I would have a dimension statement A declaring it to be 2 by 2. I can calculate the determinant as A11 into A22 minus A12 into A21 using the definition of the determinant of a 2 by 2 matrix, and I can print this determinant out. Again, I can use a format statement, and I know this is a float, so let me write it as f5.2 and 2x is simply the blank space. So let's try to calculate this determinant here. So I am calculating this determinant and you can clearly see that the determinant is coming out to be 0. And here what I've taken this particular determinant A and I've calculated it. So again it will be 1 into 4 minus 2 into 2, that is going to give me 0. So this particular matrix has a determinant of 0. It's a singular matrix and that has also come out here. So here what I did is I declared the matrix here, and here I have essentially printed out the value of the determinant, and here I have calculated the value of the determinant. Now the next thing I'm going to do is I'm going to look at what is a tensor, and a tensor is essentially a matrix which has size greater than 2. So in fact you can think of matrices vectors as tensors also. Tensors may have dimension 3, 4, 5 and so on. So what I'm going to do now is I'm going to create this tensor of dimension 3 to 2. So this is essentially a tensor. So here what I do is I form this tensor. I do I is 1 to 3, do j is 1 to 2, do k is 1 to 2, and then I write out aijk as I into j into k into 1, and then I print this particular tensor out. Now in some cases you can use a tensor. For example, if you think of three subsystems, so I would represent the three subsystems and j and k would represent matrices corresponding to each subsystem. So in that case, you can use something like a three-dimensional array, which would be a tensor. You can even have 4 dimensions, 5 dimensions, and so on. But of course, remember the size of those things are going to become pretty large. So don't use it unless you have to. So now let's turn to this tensor and try to print it out. So here I have taken the tensor and I have printed it out. So this is essentially an array in 3 dimensions and it's been printed out here. So as you would expect, it starts with 1, 1, 1 is 1 because I'm simply multiplying I, j and k. And of course 3 2 2 is going to be 12 because 3 into 2 into 2 is going to be 12. Now let us write a simple program to calculate the eigenvalues of a matrix. So again, you know that you have a matrix, let's say A 2 by 2 matrix, A11, A12, A21, A22. Then the determinant is given by this particular value being set to 0. So that would essentially entail that I take A11 minus lambda into A22 minus lambda and subtract A12 into A21 and set it to 0. This is the so-called characteristic equation. I can expand this out here. So you see this will become A11 A22 minus A11 lambda minus lambda A22 plus lambda square minus A12 A21 equal to 0. And I collect all the terms here. So lambda square is simply present here. The coefficients of lambda are these negative A11 and negative A22. And this is the constant part. So essentially I wanted to bring this to the quadratic equation form. And so now I can look at this lambda equation and I look at a typical quadratic in X and I can see the similarity here. Now, of course, what I can do is I know the solution of X here, so I can use this solution to essentially write a code out for the eigenvalues. So that's going to be formula translation. So let's do that. I have written out the equation in terms of lambda for the 2 by 2 matrix. Remember that A11, A22, A12 and A21 are the elements of the 2 by 2 matrix. And I'm going to get this equation here, and remember that there is a correlation between A being 1 here, B is this value and C is this value for the quadratic. So let's write this program. I have the matrix of dimension A 2 by 2. So I don't want to cause confusion between this small a and this matrix A, so I call these AQ, BQ and CQ. These are the coefficients of the quadratic in lambda. So a is the coefficient of lambda square, B is the coefficient of lambda, and C is the constant part here. So again, I simply copy this. So again, AQ would be 1, BQ would be negative A11 minus negative A22, and CQ would be A11 into A22 minus A12 into A21. So once I have got these values of A, B, C, I can calculate the square root part here. So that would be square root of B square minus 4ac, and then I get the two values of lambda. So again, in case all these L are there, I am converting it to float. Remember, L would be an integer, so AL would be the real. So I get the solution AL1 is this particular value and AL2 is this particular value. So these are essentially representations of minus B plus the square root by 2a and minus B minus the square root value by 2a. Now once I have done all this, I print out AL1, AL2. These are going to be the eigenvalues of the matrix concerned. So let's get the eigenvalues from first principles before we actually write the code. So again, I have taken the matrix A here, 1, 2, 2, 4. I have taken the determinant and set it equal to 0. So then I get 1 minus lambda into 4 minus lambda, that is these two, minus 4 equal to 0. I simplify it further, so I get here 4 minus lambda minus 4 lambda plus lambda square minus 4 equal to 0. There is a cancellation of 4 and minus 4. And so I get lambda square minus 5 lambda equal to 0. So this immediately gives me two roots. One root is going to be lambda equal to 0. One root is going to be lambda equal to 5 because I can write it as lambda into lambda minus 5 equal to 0. Now I wrote the program here and you can see, of course, the first part of the program I'm simply defining the A matrix. So that's the usual A matrix 1 2 2 4 given here in pink. And then the second part of the program, I essentially defined the coefficients and I obtained the eigenvalues. So the eigenvalues do come out as 5 and 0, and I have used the format statement to write it in clean form. So I have got the character string here. This has given out the eigenvalue semicolon statement here, and of course I have f 5.2 in both these cases. These have given me the floating point number up to 2 decimal places. So this is an example how the formula is kind of exactly translated into Fortran very easily. Now let's create a problem where we have complex numbers to show the capability of using complex numbers in Fortran. So what I have done here, I have taken the matrix and I have simply changed the A12 term to -10. And now let's find the eigenvalues of this matrix. So again, remember the determinant of this particular matrix with minus lambda here in A11 and A22 should be set to 0. So I expand this out. The first part is the same as before, 1 minus lambda into 4 minus lambda, but I have minus into minus 10 into 2, so this becomes plus 20 here, and I simplify this, so I get lambda square, I get minus 5 lambda, and I get 20 plus 4 is 24. So this is the characteristic equation corresponding to this matrix here. Now of course I know this equation is similar to ax square plus bx plus c equal to 0, the typical quadratic which has this solution. X is minus b plus minus root b square minus 4ac by 2a. So I can easily plug in the different values here and get the solution for the quadratic. So that's what I have done here, and so we get 5 plus minus root -71 by 2, and so here of course I have the square root of a negative number, so I get the I here. And so this particular matrix essentially has the eigenvalues given by 2.5 plus minus 4.21 times I, where I is root of -1. Now this is something which is very interesting. Let's test out the new code for this. Of course, if you use the old code for this, it's not going to work. You are going to encounter problem. You can check that out and see. So to create the code, or rather to extend the code to complex numbers, I can study my previous program, and I do realize that when we are creating the matrix, we do not have any issue with complex numbers and so on. So I just let that be the way it is. But when I come to the second part of this particular derivation, I change all these variables to complex numbers. And of course, one more thing I have done is, while the matrix has been defined typically as 1, 2, 2, 4, here I have put in the fact that A12 is -10. So what has happened is that it's essentially using this matrix. So again, once something has been formed in Fortran in this manner, you can always adjust it as follows. So after that, it does the calculation. The second part of the calculation, because I have declared all these variables to be complex numbers, the output has come out in terms of complex numbers. And you can see that as far as even the format statement is concerned, it simply treats these as floating point values. So essentially what it does is that it thinks of the complex numbers as two floating point numbers. So it doesn't care so much about the existence of I, but it knows that a complex number essentially has two parts. The first part is 2.5 here, that's the real part here you see in both the cases, and the imaginary part is going to be 4.21 and minus 4.21. So essentially you are able to get the complex root here without much problem. Now at this point, many of you may be thinking, why am I all the time declaring 2, 2, 3, 3 and so on? Basically the dimension statements are fixed, and that is what actually happens in classical Fortran, the way it was constructed. So when we were programming a long time ago in these kind of situations, what we would do is we would declare the variable size. Now this is not a problem in many engineering problems, because you do know the size of the different matrices involved in many problems, but there are situations where you may have to assemble the matrix, for example, and create matrices which have to have variable size. So you can also do that in modern Fortran. For example, here what I have done, I have used a particular statement here, and this statement you have to use. So you have to essentially say that you are creating a variable. The variable name is X. It's essentially a real variable. It's a array also, because you are saying you need some dimension here, but you're not mentioning the dimension, and you are saying it is allocatable. So this word essentially makes the compiler realize that you are going to tell it after some time what is the dimension which you do here. So essentially here I can read n and I can say that X has size n, and then I can consider this n to be a variable. So here, for example, I can write do I is 1 to n, xi is I into 1, print I xi. So let's check out this more modern code which you can use in certain situations where you want to have a matrix whose size varies with the systems which are out there or with the input which you are giving. So again, here I have given this code and I have run it with n equal to 6. So when I do that, I give the input n is 6 here. I get the output here. So essentially the do loop goes from I is 1 to 6. And so it creates a vector of size 6. That is, in this case, since I am saying that it should square this number, it essentially takes 1, 4, 9, 16, 25, and 36. And next thing I do is I repeat this with 10. So if I use n is equal to 10 here, you can see that what it is doing, it is giving me 10 values here. And so again, I am able to print these 10 values. So again, you go from 1, 4, 9. So you remember these are all the squares of the different numbers. So 9 square is 81 and so on. So again, this is something which has come up in the later versions of Fortran, for example, Fortran 90, and certainly helps in writing better code, because some things which people used to do using classical Fortran is declare matrices and vectors of very large size, and that was often not required because they may actually be using something of very small size, but they have declared, for example, matrix A of size 1000 by 1000. That is not something good in general. So now I will leave you with two homework problem which you can do, and the first problem is try to find the cross product of these two vectors I found the scalar product for. So this is certainly going to be slightly more difficult. Again, remember the cross product formulas are tied to determinants and so on, so you can easily write this kind of program. The second thing is try to find the inverse of a matrix given here. Again, that is something which will test your capability in terms of matrix manipulations and so on. So that was the tutorial for today. So now you are familiar with aspects of vectors, matrices, even tensors as far as Fortran is concerned. And you realize that it is actually very simple. You can create these kind of vectors, matrices, and tensors by using the dimension statements. And you can also create situations where you have a variable size matrix and vector and tensor and so on. So today I will stop here and I will leave some videos on the end screen which you can check out further to continue your journey into education, programming and research. And in the next lecture, I'm going to look at things such as functions. So how you use functions and maybe even subroutines in Fortran. Maybe I'll create two tutorials on each of these topics. And if you have any comments, do leave them in the comment section, because as you know, YouTube likes comments. So if you leave them, YouTube will think that this particular tutorial is more important and it will help many people learn more about Fortran.